Okay, so far, we've been talking about this frequency response. We are getting into behavior of the system in response to some sort of sinusoidal or exponential, unitary exponentials. And now the next stage in that really is looking at Fourier series and Fourier transform. So you can see that it naturally leads to that. So let's start with something that you're familiar with, which is the Fourier series, right? What is Fourier series? Anyone can explain Fourier series to me? Any thoughts on how do you describe Fourier series? Yes?
Basically, like, given any arbitrary, like, periodic function, you can decompose it into, like, a weighted sum, a linear combination of, like, complex exponentials.
Well, complex exponentials, cosines and sines, which are the same thing, right? So yes, exactly. So it says you can write a periodic function as a weighted sum of sines and cosines or exponentials. And by the way, Fourier had an interesting story. There's an interesting story about Fourier. So by the way, this concept was known before Fourier. This is actually, you can find this concept in the 3 BC stuff. Astronomers and things of that sort used this for 3 or 4 sines and cosine. But they didn't know that any function can be written. They knew that such many functions could be written. But anyway, so Fourier kind of wrote it in a more general sense. And Fourier was an engineer, right? So Fourier came and did this and produced this result and then presented to the French Academy. But he got a tough kind of review committee. He had the Lagrange, Laplace, and Legendre. These are really tough group of hardcore mathematicians. So this is not rigorous. This is just, it doesn't make any sense. There's no proof here. There's so many missing pieces also. So there was apparently a prize that he also submitted his paper to. So then at that point, Napoleon intervened. They said, oh, this is not, by the way, Napoleon was a very good in mathematics. I don't know if you know this or not. He was like top of his class in math. But now he intervened and said, I don't care what you guys say. He makes excellent cannons. Give him the prize. So he did it for heat transfer equations and all those things. It's the first time Fourier did it and all those things. So, but anyway, so that's an interesting story. Engineers are rewarded differently. Anyway, so what is the Fourier series? So let's think about the Fourier series. Right? So we said it's a weighted sum. So if you have a periodic function with a period of t, then you can, if you find a working marker, you can write it as, x of t, let's say. So x of t is periodic. X of t is equal to x of t plus nt. And then you can write it as the sum of, you can write it as a0 over 2 plus sum of n1 to infinity of an cosine of n omega naught t plus bn sine of n omega naught t. Right? So you can write it as a general, in the most general form, as sums of sines and cosines. And these an and bn's can be calculated in the following form. So an's are 2 over t, where t is the period, integral over 1 period of the function, times cosine of n omega naught t dt. And bn's are 2 over t, integral from negative t over 2 to t over 2 of x of t sine of n omega 0 t dt. Now, so this is the basic calculation, right? What it really is, it's another way of to think about it, is that the space of these, if you want to talk a little bit more mathematically, you can say the space of these periodic waveforms can be spanned and can be described with these basis functions. So these are the basis functions. The cosines and sines are basis function for that space. So you can actually write any element in that vector space as the weighted sum of these things. So that's what it says. I mean, kind of roughly speaking, there's a lot of, again, mathematical nuances that we are not going to go into because that's not what we are interested in right now. So if you start with this now and then say, okay, you can also do something else. We realize that cosine and sines are essentially, let's see, one good black marker. So cosine of n omega naught t, we know we can write it in terms of exponentials, right? So we can write it as e to the j n omega naught t plus e to the negative j n omega naught t over 2. And we know that the sign similarly can be written as e to the j n omega naught t minus e to the negative j n omega naught t over 2j. So what that says is that now I can plug these into this guy and see what I get. Because if I plug it in there, then x of t can be written as a0 over 2 plus, then I have the an and bn's in that form. So I have an e to the j n omega naught t plus e to the negative j n omega naught t over 2 plus bn e to the j n omega naught t minus e to the negative j n omega naught t over 2j. I keep the 2, I take the j and put a minus sign in front. So that's the sum from 1 to infinity for this thing. Now you can see that I can get these to, I can put these e to the j n negative e to the j n omega naught t's together and e to the j negative j n omega naught t's together, right? So I can reorder this, and then when I do that, I can you can easily see that I can write this whole thing as some Cn e to the j n omega naught t with n going from negative infinity to positive infinity, where Cn's are essentially an minus jbn over 2. And C0 is A0 over 2. So now you can actually see that you can write this also as the sum of just exponential, like you said earlier, right? So you can actually write it in this form of the sum. And it's not that difficult to see. And you can see that Cn conjugate is C negative n. So they are the conjugates of each other. C of negative 2 and 2 are complex conjugates of each other. So you can write any function, you can express any function with this sum where Cn's are coefficients, complex coefficients, but with this property that they are the C of n and C of negative n are complex conjugates of each other. So they're not any arbitrary Cn's in this case if you want to have a real function. If you have a generally non-real function, then you can get other things. And also equivalently, you can easily see from this expression, if you plug these two, use these integrals and plug them in there, you can see what Cn's are. So what you can do, you take this definition of an and plug it in here, and this definition of bn and plug it in there. And what you will end up is you clearly see gets cosines minus j sines, and that what would it do is that it says you have Cn's are essentially 1 over t integral from negative t over 2 to t over 2 of x of t e to the negative j n omega naught t dt. It's very straightforward to see. This 1 half cancels that 2. Then you have a cosine and a sine and a j. And it's basically becomes cosine negative j sine, which produces the e to the negative j n omega naught t. So this is how Cn coefficients are calculated. So this is the basis of the Fourier series. And what this really means, the question is really the interpretation of this thing. One way to think about it is that think about these. You can plot these quantities of Cn's versus n, right? So this would be 0, 1, 2, 3. You can basically say at 0 I have this value. You can just have like this bar charts, if you will. And of course, the magnitudes of the Cn's have to be the same because this should be symmetrical because these are complex conjugates of each other. So try to make it as symmetrical as possible. So you could do it versus n, where basically it shows you 0, 1, 2, 3, 4, and these are values. So this is C0, this is C1, C2, C3, etc., etc. And C negative 1. Or you could just say, look, this is omega, and this is omega naught, this is 2 omega naught, 3 omega naught, and so on and so forth, negative omega naught, negative 2 omega naught, etc., etc. So what does this plot really show you? What does it tell you? It gives you a sense of how strong each one of these frequency components are in this periodic waveform, right? So you can see in this example, you have a large third harmonic, you have a large fundamental, which is sometimes people call it first harmonic, which is just the fundamental of the first harmonic. Second harmonic is smaller, and all those things. And by the way, this is something that also defines the sound of a musical instrument. The reason, for example, that a middle A on a piano, on a violin, on a a trumpet or anything has the same fundamental frequency. And as such, since it's a periodic signal, also their harmonics are the same. So they are the same exact frequencies. So why is it that they sound very different? It's just the ratios of these harmonics that's different. And how the blend of this harmonic is different and gives it a different sound. So that's what makes the sound of a piano different from a violin, from a trumpet, or from anything, right? From a flute or what have you. So this is actually interesting. So because these are really what we call frequency components. How much of each one of these you have in your spectrum. So this is interesting. Now, but one interesting question about this is that so these are really applicable to periodic waveforms, right? Now, what do you do if you had an aperiodic waveform? What do you do with that? Is there something we can do with an aperiodic waveform? Yes? Okay, so he says take the integral from minus infinity to infinity. Right, but why? What is the justification for that?
Because if it's aperiodic, then its entire period is just over all of
Exactly. So he says if it's aperiodic, the entire period is like that. Another way to think about it, another way to say exactly the same thing is an aperiodic signal can be thought as a periodic waveform with a very, very long period. You can just imagine that this entire thing will repeat. And you say, well, wait a second, this will not happen. You can think about the entire life of the universe as the period. And you say, all of this has happened before and all of this will happen again. And you repeat it, the same thing, right? And then even at that point, you can say, okay, this is a periodic. So if it's aperiodic, it really is like something with a long period. Now, what does a period do to this plot? If you think about it, if the period becomes larger. So what is omega naught? Omega naught is obviously 2 pi over t, right? By definition. Which I don't think we ever defined it, but yeah, it's very clear. 2 pi over t. So as I increase t, what happens to my omega naught? Becomes smaller, right? So what happens to this plot? It becomes denser and denser, right? These frequency components that were discrete, they become closer and closer and closer and closer and closer to each other. So in the limit, what do you get? You get a continuous function. You should expect to get a continuous function. So that's the concept of a Fourier transform. A Fourier transform is just a Fourier series when you look at a very long period, and as a result, instead of having individual distinct frequency component, you will have a continuum of frequencies. So that's a qualitative way of saying it. You can make it actually more quantitative, right? So you can actually write it, so there are different ways to make it quantitative, which gives you different interpretations. So we'll start with one. So x of t, we said earlier, we determined that could be written as the sum of Cn e to the negative j n omega naught t, for n equals negative infinity to positive infinity. Right? So now, with that in mind, now also keep something else in mind. So this is, or you could also write it, we could also write it in terms of the actual frequency, the f. So we can write it as 2 pi f naught t. So now I'm going to play a little trick here. I'm going to use this property. So I use the sifting property of the deltas, j2 pi n f naught t, right? Do you agree that this can be written in the form of this integral? Do you remember the sifting property of the delta, of the Dirac delta? What it did, it just pulled the value of that function at the point where its argument became 0. Right? So its argument becomes 0 when f is equal nf naught. So it pulls the value of this function, which is this at that point. So this one doesn't have an n in it, and f is a continuous function, right? So that's basically the way. So I will use this and plug it into that sum. Let's see what happens. So if I use it and plug it into that sum, so I will let's just write it as such. It would become the integral from negative infinity to positive infinity of e to the negative j 2 pi f t delta of t minus f minus n f naught df. Okay, so I will change the order of this summation and integration. I try to take this integral out, and I'm going to push the sum in. And when I do that, of course, I can take anything that's not a function of n outside the sum. So what are the things that are not functions of n? Well, df is not a function of f. I have the e to the negative j 2 pi ft. That's not a function of n. So what I'm left with is going to be this, Cn, n equals from negative infinity to positive infinity of delta of f minus n f naught. Right? So that's x of t. But now, look at this quantity. This is just a function of f, right? This is basically, what is this? This, if you think about it, this is a function that has multiple impulses at different locations with the values of Cn as their areas. So these are multiple Dirac deltas that are scaled by Cn. So this is C0 sometimes Dirac delta, this is C1, C2, C3, C4, C5, and so on and so forth, as a function of f. So the x-axis is f. These are happening at f naught, 2f naught, 3f naught, so on and so forth. F naught, 2f naught. So the spacing of these things is f naught. So this is that function, right? Let's call this function, I call this function capital X of f. So this is capital X of f. So it's a function that has all of these impulses. You can see it's the sum of all these impulses weighted and shifted. Shifted by different values and weighted with different values, Cn's, and shifted by different multiples of f naught. Right? So this function, this new function x of f, is what it is. So if I use it that way, I can write x of t as the integral from negative infinity to positive infinity of x of f e to the negative j 2 pi ft df. Now, this is really what we call the inverse. This is Fourier transform, but it's really, to be more accurate, this is the inverse Fourier transform of x of t. So we call this the inverse Fourier transform. Now, the interesting thing about it is that the way you calculate this from that expression is, you can easily show that it's actually x of f is now also, as you can also see in that term, Cn is going to be x of t e to the j 2 pi ft the plus df. And this is the Fourier transform of x of, inverse transform of x of f, x of t. This is capital X of f. So this is the Fourier transform, and this is the inverse Fourier transform. You got both of them here. Now, why is this interesting? First of all, by the way, look at this and see if it reminds you of something, this transform. That's something that we did earlier. What does it look like? Laplace transform. The only difference is what? S has been replaced with 2 pi f, or j omega, right? If you say S is j omega, which is basically j 2 pi f, and if you look at Laplace transform, you remember the Laplace transform of x of t was the integral from negative infinity to positive infinity of x of t e to the negative st dt. So you can see that this is, if this were x of s, that x of s is really the x of j omega, or x of j 2 pi f. So they are one and the same. So the Fourier transform is a special case of Laplace transform when you look at it only on the j omega axis. Right? And because you are limiting it, because you're looking at a special case of it, it allows you to also get the inverse, which is essentially the same, except for a change in sign. So its inverse Fourier transform, its inverse is the same as its function. This should be dt, obviously. Right? So this is the Fourier transform, and this is the inverse Fourier transform, which is really the limit of Fourier series when you're essentially when you go to when you make your period very long, and as these start collapsing. Another way to see that is the following. Think about what we wrote up there. X of t is the integral from negative infinity to positive infinity of x of f, capital X of f, e to the negative j 2 pi ft df. Now, this is an integral, right? But you can approximate an integral, you remember we've done this several times in the past, as a sum, right? So how do you approximate an integral as the sum? Let's write this in omega, so to make our lives a little bit easier. You can also write, so if you write it in omega, if I want to write it in terms of omega instead of t and make this d omega, would this change? There will be one little change I need to make, right? If I want to go from the expression for the f, which looks like that, to an expression for omega, if I want to do a change of variable from f to omega, if I say omega is 2 pi f, would the Fourier transform be defined exactly this way? Say again? 1 over 2 pi, exactly. So you need a 1 over 2 pi up front. So if you write it in terms of omega, it's 1 over 2 pi. That's why I prefer to write it in terms of f, if you get a chance. Because when you write it in f, it becomes completely symmetrical. I don't have to worry about 1 over 2 pi, which one had the 1 over 2 pi, which one didn't. Yes?
Should we also scale x of f to x of omega?
Yeah, it should be x of omega. But it would just basically be another function, right? Since f is a function of omega. You're right. Right? It's a function. I can express it as a function of another function. So that basically becomes the x of t. Now, if I write it this way, so I wanted to take this integral and approximate it with a sum. So when you take an integral and approximate it with a sum, what do? You look at the d omega, which were these infinitesimal steps in omega, and make them finite, right? So let's call those steps omega naughts, right? If you make those steps omega naughts, then I have to span the space of omega naught. So I can write it as a sum of n from negative infinity to positive infinity of e to the negative j n omega naught t to span the space with this sum, right? So I want to go in steps of omega naught from negative infinity to positive infinity. So n goes from negative infinity to positive infinity times omega naught spans the omega. And then I have omega naught, which is this. And then I have x of omega over 2 pi. right? Well, it's not x of omega really anymore because it's sum. So it's x of n omega naught. I can actually absorb this omega naught and put it up front here. So what does this look like though now? This description of x of t. Doesn't it look exactly like this? And this was a negative one, by the way. Yeah. Yeah. Yes, that's a negative. Oh no, actually that's not a negative. Don't change. Sorry, doesn't matter. Doesn't matter. It's not. It doesn't matter really. Just keep this positive, so we don't want to mess with that. So that was good. It's just the order of the sum, how we calculate it, right? Just we can go from one side to the other. So, but anyway, it's the same thing. Because you have both the negative ones and the positive ones. So that was okay. And this one, but doesn't it look like that? If I just call this Cn, or if you want to be more accurate, I can call this C negative n, right? If I call this C negative n, then this sum becomes just Cn e to the jn omega naught t. Right? So you can see that in a special case, it really reduces to what you had before, which was this, which was correct. Right? So that tells you something about it, right? I mean, that tells you that this Fourier transform is really a generalization of the Fourier series. So that's fine, but this is the basic definition of the Fourier transform. So maybe we should do maybe a couple of examples to see how it looks like. And we'll do more examples as we go forward. So let's do an example here. So what is the Fourier transform of, let's say, x of t is 1? What's the Fourier transform of 1? How do we do that? Well, let's use the definition. So x of f, right? Did I do x of f or x of omega? I did x of, well, I've done the other one, but so let's do the inverse Fourier transform first. X of f, and I want, so x of f, capital X of f is 1. Let's say the Fourier transform is 1. I want to say what function produces the Fourier transform of 1. Let's see what it does. And we'll get to the other side too. We'll do the opposite one too. So x of t was the inverse Fourier transform, right? So what is the inverse Fourier transform? It's an integral from negative infinity to positive infinity of x of f e to the negative j 2 pi ft df. Now x of f is 1. So this becomes integral from negative infinity to positive infinity of e to the negative j 2 pi ft dt. What is this? How do you calculate this integral? Well, let's do this. Let's do something. Let's write it this way. Do you agree that I can write it as a finite integral from negative a to positive a? Or should I do a over 2? Yeah, a, that's fine. Of e to the negative j omega t dt. I'm sorry, df. D omega, well, d omega. And this would be df, which I can write as d omega. And I put the 2 pi up front. Right? If I switch to omega, I just basically have to put the 2 pi up front because of the change of variable. I went from df to d omega, so you get a 2 pi. So what is this integral? Can we calculate this integral? This should not be that difficult, right? What is that integral? So you get the 1 over 2 pi. Now you get negative 1 over j omega, or negative 1 over jt actually. Negative, so you get negative jt, and then you have e to the negative j omega a minus, or I'm sorry, jat minus e to the negative JAT. Or I could absorb this minus sign into here and make this negative, make this positive. Make this positive, make this negative. Oh, sorry, the limit of that. Limit of a going to infinity of e to the JAT minus e to the negative JAT. So what is that quantity, by the way? Is it something that you're familiar with? E to the j something minus e to the negative j something. What if I take this 2j and put bring that in? So take this 2j out of here and put it there. Does this look familiar? Sine of what? So let's write it here. So what is that? I have 1 over pi t. It's this. So maybe I can actually even take the t and put it in, right? So if I put the t in there, is that the sign now? Is it? Or is it not? So let's not do that. So it's the sine of what exactly? Sine of AT, right? So sine of AT, it's the limit of this thing, sine of AT, when a is going to infinity. Now if I bring this in, what do I get? Did I miss something? Okay, no. So let's do something. I can multiply and divide by a, right? Pi t. Let me just double check something here. I think I may have made a little mistake. Pi t. So yeah, let's put that inside the limit. Oh yeah, that's correct. Okay. So I can keep these inside the limit. Doesn't matter. So I can do the limit of a goes to infinity of this pi t. Now, okay, so let's write this slightly differently. So this is the limit of a going to infinity of, now I'm going to multiply and divide by a. So I get a over pi, and then I get sine of at over at. Now, what is this function? Are you familiar with this function? It's called the sinc function, sine of x over x. So sinc of x is defined as sine of x over x. And what that is that, so this becomes sinc of at. Do you know how the sinc looks like? Sinc of x? Have you seen it before? It's actually an interesting function. So sinc of x is defined really as sine of x over x when x is not 0, and it's defined as 1 when x is 0. And if you look at it, it looks exactly like this. It's a continuous function. Looks like that. Because it's a sign that as x becomes larger, scales down. So, and why is the value of 1 here reasonable? Because what is the limit? Do you know the limit of this when x goes to 0? 1, right? So we've set the value to the limit, which basically makes it continuous. So this function is an interesting function because at this point, in general, if you have a sinc of at, is when this sign first becomes 0. So when this becomes pi. So at equals pi. So in other words, t equals pi over a. Okay? Now, what is the area of this thing? Now, as you can see, as I'm increasing a, what happens? So let's say now we are looking at this limit, right? As I increase A, what happens to this side? A is larger, so then it becomes narrower, right? Now, what happens to its height? Now, its height really in this case, because of this, is A over pi. So it becomes narrower, but its height is increasing. It's scaled up. As it becomes narrower, the area scales down by A. But as its height is increasing, the area scales up by A. So what do you think this is? Delta. Yes?
So since the Fourier transform is a special case of Laplace transform,
Since Fourier transform is a special case of Laplace transform.
just grab that table.
Yes, we could. We could. Yeah, absolutely. Now, I wanted to say that you said so. You basically the question is that if since the Laplace transform is a special case of Fourier transform is a special case of Laplace transform, couldn't we use the table that we already had instead of going through all of these calculations? And we could, but we wouldn't have seen the sink shrinking and this impulse growing, and seeing why it happens. But yes, you're right. You could have done a shortcut. The same thing that we could have calculated convolutions from the beginning with multiplications, but we don't because we want to understand that process before we compress it and condense it into something simpler that we can handle. Because still we need to know what we've done. So this is interesting, right? Because now you've seen that the Fourier transform of delta of t is x of t, is 1, which actually would have been a lot easier to go from directly. Right? If I make x of t, delta of t, what do I get? Because the value of this thing only matters at t equals 0, which is 1. So it's the integral of the delta, which gives you the 1. So we went the long way around to show this. But this is actually probably even a better way of defining an impulse. It's a smooth function that just becomes narrower and sharper. Now, the other interesting thing to take away from this is that, and we'll talk about this more, is that you can see that as you make, so you started with something that was very wide in frequency. It corresponded to very narrow in frequency. You remember when we said impulse has all the frequencies, it excites all the frequencies? This is how you can see it. The Fourier transform of an impulse is 1. It has equal frequency components at all frequencies. So it excites all frequencies equally. That's why it brought all the natural properties of the system out in a natural way. So we'll talk about this more next time. Any questions? No? All right, well, I'll see you next time.